Hi, myself Naveen Kumar Saini. In the course Electromagnetic Field Theory, code KE301. So, in the extension of the last lecture 13, we have come to lecture number 14, in which we will continue with the applications of the Ampere's circuital law. So, here the third application is the infinitely long coaxial transmission line. So, in that, in the previous two examples or two applications, we have discussed about the line finding the value of H when we have the current carrying conductor, and second application we have covered when we have the sheet current, then we found the value of H. So in the next one we have the infinitely long coaxial transmission line, in which the question arises what is the value of H everywhere. So overall question is we want to find the value of H everywhere, right? So this is the question. So it means we have the coaxial cable. So this when you see the coaxial cable from the front side, so this, if it looks the coaxial cable like this. So this coaxial cable, we have two materials in which the different permeability is there for that, this one and this one. If you want to find the value of H, so it means what are the possible cases or the areas on which we can find the value of H. So first one is this one. We can find the value of H at this low point. Second value of H we can find outside of this material. Third value of H can be find out within the next material. Fourth value of the H can be find out onto this, right, outside the complete coaxial cable. So the assumption here which we are assuming that the current inside the conductor is I, right? So we are looking at positive Z direction. So it is representing the positive Z direction. So within the, just like this, so we have the within the conductor, within that material, we have the value of current which is outside. So which we have the next lapping of the material. So in which the direction of I will be opposite direction. Why it is so? Because to close the circuit, right, to close the circuit, inside material current will be in outside, and the outside of that material we have the next material in which direction of current will be opposite direction. So this is the I, this is minus of I. Okay, assumption is value of Z. Assumption is current, this current carrying conductor, these are lying on the Z axis. So to mathematically we can represent it, the value, determine the value of H everywhere. So for that, what are the areas on which we want to find the value of H? Here. So this is the point, right? If we want to find the value of H here, so it means we have to draw the Amperean path for this case. Okay, Amperean path for this case. So what is this range of length here? This range is from this point to this point, so 0 to A. So here we are representing the rho. So rho is the, because in cylindrical coordinate system, rho is what? This is the radius of the cylinder. So rho range will be 0 to A. Second value of H we want to find here. So for that one, again we have to find the Amperean path. So this is the Amperean path, L2. So in this, the range of length will be what? It will be from this point to this point. So what is this point? This is the rho. This is the this is the A, this is the B. So rho is from A to B. Then third Amperean path which we can draw, this is in this direction, right? So this is in the next magnetic material in which we can find the value of H. So for that one we have to draw the Amperean path, that is L3. So what is the range for this length for the L3 path? So this will be from here to here. So how to represent that? This is from here to this point. This is the B to up to here. So what is this? This is nothing but the B plus T. T is what? T is the T is this one. This is the width of the cable, right? So this is the width of this magnetic material. So this is the rho will be B to B plus T. Next is the last value of H, which is outside this cable, this one. So again we have to draw the Amperean path for this, right? So this is the path L4. So it means we want to find the value of h somewhere here. Okay, so for that one, what is the range of that? So the range of that is rho is greater than this one. Rho is greater than this one. So what is this? This is up to b, and this is b t. So this is completely from here to here. This is the b plus t. So this is your b plus t length. So it means outside this one it will be rho greater than b plus t. Here. So these are the four possible areas in the space from in which we can find the value of h. Okay, so we will take one by one, so that things must be clear to all of you what is the things, and by using the Ampere's circuital law. So we will use Ampere's circuital law to find the value of h. So here the first case which we have, rho is 0 to a. So for this case, just apply the Ampere's circuital law. Same formula which we have derived, which we have discussed in the first case, that is h dot dl is equal to I enclose, and I enclose is nothing but j dot ds. So these expressions we have already discussed in detail in the last lecture, how we get this one. So we simply apply the Ampere's circuital law for that. Okay, so what is our main concern? Main concern is to find the value of h. Okay, so I enclose is there, j dot ds. So we are in the path 1. So we are talking about that. So it means we have to take the value of j and ds, cross-sectional areas. So for that, j is equal to what? So for this case, j is equal to I upon pi a square, and az, obviously the direction of this one is z, and ds, because this is your cylindrical coordinate system. In the cylindrical coordinate system, so what is constant for this case? For this one, a is constant. Okay, so a or the z is constant. So in this case, what is the area, what will left? So three elements which we have discussed already about the ds. It is can be your d rho or rho d phi, or it can be your d rho dz, or it can be your rho d phi dz. Okay, so when we are talking about this one, so here we can see this one, the direction of this one is az, direction of this one is a phi, direction of this one will be what? A rho, right? So which case we are talking about? We are talking about this one. So for this one, ds is this, ds is equal to rho d phi d rho az. Simply multiply this one, then we will get the value of I enclose. So this I enclose is nothing but, so it is shifted here, so it is I upon pi a square. So the limits for ds will be what? So limits for this, which we have to take it about, the limits for rho and limits for phi. Because this is circular, so it means the limits for phi will be what? 0 to 2 pi. But when we have the radius of, we are taking care about the radius rho, so this one will be 0 to rho. So here we can see we are taking this one 0 to rho. So this rho is variable. This rho will vary from here 0 to up to here. Okay. But when this is the current, we are enclosing this current, right? We are enclosing this current only. That is why we are taking the range 0 to rho. So that is why we are taking the range 0 to rho. So when we solve it, then we will get the I rho square upon a square. Then h phi dl. So dl will be what for this case? Dl is the path length. So this path length can be find out by our this value, that is 2 pi into rho. So 2 pi into rho is into h phi. So this expression we are getting from here. So just put it all together. So these things just put it into this equation. Then the value of h phi will be I rho upon 2 pi a square. So I rho upon 2 pi a square. So this is the value of h at this point. So this at every point on this Amperean path, value of h phi will be same. That is I rho into 2 pi into a rho. Okay, so in the vector form we can represent it. How we can represent in the vector form? So this will be vector of h is equal to I rho upon 2 pi a square into a phi. So this is the component, this is the vector. Second region is rho a to b. So this is the region from a to b. So in this the path L2 is we have to consider. So for this path, what is the total current which is enclosed? enclosed current will be what? This is this one. Total current, which is what? This is the I enclosed. So here that is why we have taken the I enclosed is equal to I. And now again, this is a very simple case as we have discussed about the infinite line current. So the expression which we got for the infinite line current, the same expression we will get it for the infinite line current here itself. So this value will be h dot dl I enclosed. So in place of h dot dl, we can write the h phi into 2 pi rho. So rho is the obviously variable 0 to rho. So it will always vary. So now the value of h phi will be I upon 2 pi rho. So this is the same expression which we got it when we had discussed about the Biot-Savart's law and their applications for the infinite line current. So I upon 2 pi rho. So just keep in mind about all these things. The range for that one is A to B, from here to here. Now come to the third case, which we have the rho is 0 to B, B to B plus T. So this is the L3 path. So this is our L3 path for that. So in this we can see for the L3 path, what is the total current enclosed. So total current enclosed for this one will be what? Current I plus current enclosed by this surface. Current enclosed by this surface up to here, right? Overall current enclosed for this. So how to find I is from here, and how to find the current enclosed at this point? We have to use the J dot ds. So what is the formula in this case? Total current will be equal to I plus J dot ds for this surface. So here I enclosed is equal to I plus J dot ds. Okay. So I is okay, no issues with it, but we have a J dot ds. So J dot ds again, what is that formula for that? That is pi, I upon J, right? So for this one, what we have the formula, that is I upon pi. Maybe just some of the example we can take R square, right? So R is what? R is the radius for that. If we have the cylinder, then we will take 0 to R. But when we have the sections of that, then we have to take the limits for this, like here. So L3 path is varying from this point to this point for L3 path, right? So from this point to this point. So what is this point? This is the B plus T, and here this is the B, right? So it means if we want this one, so this is the T, sorry. So in this case, when we want this one, so how we can find out? We have to take the area from B plus T from here minus the area for this one. Then only we will get this section. Okay. So same thing is applied here. I upon B plus T whole square minus B square. And the direction of this one is AZ. Okay. So just when you put all values all together into this equation, then it will, after solving this, then the value of I enclosed will be this much. So I will suggest you that please go through it, how to find the value I enclosed. And these are very simple calculations, so where the limits 0 to 2 pi and B to rho is there. Then after solving this, H phi will be is equal to I upon 2 pi rho 1 minus rho square minus B square upon T square plus 2BT. Okay, so this is the case when for the L3 path. Now we come to the for the L4 path. So for the L4 path, total current enclosed will be what? So this is plus I direction, this is minus I direction. So it means when you find the total current for this L4 path, so in this case it will be plus I minus I. So that is the 0. So total current will be I minus I is equal to 0, and that is equal to H dot dl. So again, so length cannot be 0. So what left? Only H phi, or the H phi component will be 0. Okay. So H phi is 0 outside the coaxial cable, right? So it shows that when we have the total current which is enclosed by this outside the cable, so it means total current will always be 0. Net current always be 0 in this case. So all these things, all the expressions which we have find out in the last previous slides, so we can combine all these things all together. With the help of this diagram, we can understand that. So this is our main these are our main picture through which we have found the value of H, and these are the values based on these ranges, right? Based on these ranges, we found these things. So here we can see that when we have 0 to A, rho is 0 to A, so we can see that H is directly proportional to the rho, right? So this is a linear, so that is why we have taken the from 0 to A. So up to A, this value is I upon 2 pi A. After that, H is inversely proportional to rho. So that is why we are taking the inversely proportional here, right? Then we have h5 for the limits from b to b plus t. So this rho will be inversely proportional to rho, and this is a rho square. So these are components which are there. So it will be more, because with the minus sign, so this is more diverted to the towards the 0. So at this point at b plus t, this value h5 will become 0. So that is why they have come to the downwards. Okay. So after b plus t, rho is equal to rho greater than equal to b plus t, what is the value? So h5 is 0 obviously. So up to here the h5 value will be 0. So this is the complete result of the infinitely long coaxial transmission line, which is coming from this diagram which we have just covered, right? I hope all the three applications of the Ampere circuit law is clear to all of you. If you found any difficulty, please mention it on the chat window. The next topic, which is very easy, that is the magnetic flux density. So this magnetic flux density is just a property of the material through which the flux lines are passing through it, or the magnetic flux intensity is passing through it, right? So in that, just like the electric flux density and the electric field intensity are related with the formula, that is D is equal to epsilon naught E. So similar to that, in the magnetic field, we have the magnetic flux density B is equal to mu naught into H. This is a relation between the B and H here. So mu naught is nothing but this is the permeability of the free space, and the value of that one is the mu naught is equal to 4 pi into 10 to the power 7 Henry per meter. Okay, as we have discussed in the electrostatics, where we have finding out the value of epsilon naught, so that unit was farad per meter. Okay, but in the case of magnetic field, the unit is H Henry per meter for the permeability, and that time there was a permittivity, and the differences between these two, their functionality and how we define the mediums. So this we have discussed already in the previous lectures. Next, a magnetic flux through the surface is given by psi is equal to b dot ds. This is very simple phenomena where we see when we have the Venus surface and we have the magnetic source here, so and then this magnetic source is passing through this surface. So how to find what the total flux is passing through this given surface? So for that one, we have the formula, that is B into ds. ds is what? This is the total, this is the elemental surface on the surface, right? Elemental surface area on this surface. So we have to integrate this surface only to find the total flux line which is enclosing by this surface. So this value phi is equal to b dot ds. B is what? B is nothing but these are flux lines. So the flux lines have a different source of generation of the flux line which is passing through the surface. So psi is the Weber's. So these are intermediate standard things which you have already you have gone through it in the previous cases. So here B, that is the Weber per meter square or the Teslas. So these things are very much must be clear to all of you. Magnetic flux lines, which is a path to which B is tangential at every point on the line. And each flux line is obviously closed. So there is a north and south poles, and the north pole is the source for generation of the magnetic field, and the south pole is the sink for the for diverging, or you can say this is sinking towards the south pole only. Okay, so it is representing the direction of the magnetic field, which I have just said. When you're holding the current carrying conductor into this way, and the direction of current will be direction of thumb. So and then the direction of these fingers are representing the direction of H or direction of B. So these are the flux lines, and here these are simply representations so that you can understand easily how the north and south poles, north and south poles are acting, where the north pole is source and south pole is the sink for the magnetic flux lines. So same representation. These are the 10th standard things which you have gone through already for some of the experiments we have seen. So here the important point is here now. So with the comparison point of view, when we have in electrostatic, we have the charges, right? So as I said previously, when we have the charge, so there is the aura of that charge, we call it as the electric field, simple. So in that can be the positive charges or the negative charge. When we have the positive charge, so this positive charge can be act as a source through which the electric fields are generated. When we have the negative charge, so we say this is the sink of the electric fields lines, right? In the case of the when we have the magnetic poles, north and south poles, there is no, in these poles are just used for the emanating the flux lines and sinking the flux lines. So there is no monopoles exist into the magnetic materials, right? So this is the directions of the magnetic fields which is passing through, which is going out from the north pole and is coming into the south pole. So whenever you draw this any surface or closed surface, so in the closed surface, whatever the flux lines is going out, so the same number of flux lines will go in. So that is why the net flux lines into the given volume will be always be zero. So that is why in the magnetic field there is no monopole exist in the magnetic field, but there is a monopoles exist in the case of the electric field, right? Next point is to take care about the psi. These are total flux lines, which is equal to d dot ds, that is charge enclosed by the given surface. But in the case of magnetic field, psi is equal to b dot ds, where it is representing, because as I said, there is no monopole exist into the magnetic field in the magnetic dipoles. So it means net flux is going in, same flux is going inside to the south through the south pole. So it means net flux enclosed by this given volume will be zero. So that is why we are taking that psi is equal to b dot ds equal to 0. Okay. So these are just simply representation of the different poles when you are cutting all this complete magnet into small sections. So again, all the time you will get the north and south pole. Okay. So it shows the broken magnet, how when you block it, then same thing will be occurring to it. The Gauss law for that is b dot ds is equal to 0. So when you are applying, so we have just discussed about this b dot ds when we have a closed surface that is equal to 0. So just simply apply the divergence theorem. So that is a b dot ds equal to del dot b into dv is equal to 0. So when you compare these two terms, left and right hand side, then del dot b is equal to 0. So this is the conclusion for the Maxwell's fourth equation, del dot b is equal to 0. It shows that there is no isolated poles exist, right? So I hope we have covered till now all the Maxwell's equation number 1, 2, 3, 4. Del dot d is equal to rho v, del cross E is equal to 0, del dot b is equal to 0, and next, that is which we will discuss in the next lecture, fourth equation in the next section, del cross H is equal to I. I hope this point all clear to all of you. So in the next lecture, we will continue with the again Maxwell's equations. Thank you very much.